Hello everyone. On behalf of Saint-Gobain, thank you for joining this webinar and taking time to be with us today. I'm very excited to share with you today information about how designing acoustic in industry. This webinar is presented by the Central Team Technical Insulation of Saint-Gobain is over. For your information, this session will be recorded and shared through our social media, so you will be able to have a look back on it. I also invite you to put any question you may have during this session. Thanks to the Wizambly application, the necessary QR code will be shared in the next slide. Then we will open a dedicated Q&A session at the end of the webinar. We'll be today two presenters, and without any more delay, I let know the floor to my colleague Edouard, who will be my best support today, thanks to his strong experience on these matters. Edouard, the floor is yours.
Thank you, Fabien, for this introduction. Hello, everyone. My name is Edward van Engelhoven. I work for Saint-Gobain Technical Insulation in the Benelux, and I have a role as Technical Project Manager for Industry, which means I help with the specification of technical insulation system in industry, mainly thermal insulation system and also acoustic insulation systems. And being here today is a real honor, especially with my colleague Fabien. Fabien, the floor is yours.
Yes, hello everyone. I'm Fabien KERVEADOU. I'm working as a system manager for the technical insulation central team of Saint-Gobain since now 2019. I have almost 10 years of experience in insulation product, with 4 directly dedicated to technical insulation and industry. I have a different role inside the central organization, but I'm mostly dedicated to R&D activity linked to development of new solutions for corrosion under insulation and also acoustic, of course. 2 topics to be tackled in industry area. I just let the slide just few seconds more, just for you to scan the QR code that you have in the top right side of your screen. Okay, let's start this webinar by introducing first our technical insulation central team. We deliver insulation solutions to customers since 1937 across all technical markets, from marine to industry, HVAC, automotive, and household appliances. Of course, the today webinar will focus on the industry sector, but for you to know, webinars are coming up for all our different markets. So please stay informed through our social media to receive the last information. We have an expertise in a wide range of material with a multi-material offer, from glass wool, stone wool, but also our premium stone wool ultimate, which is a lightweight, flexible, and offers the best-in-class thermal performances. And for your information, more recently, we have now integrated elastomeric foam inside our portfolio, which allow us to cover all temperature ranges observed in the industry area, from cryogenic temperature to very high temperature up to 700 degrees. This webinar will be dedicated, of course, to noise control in the Pipework application, in red on your screen. But for you to know, we have also developed a wide range of solutions for acoustic industry with a focus on 7 different applications that you have actually on your screen. Let's discover our today's agenda. The part 1 and 2 will be mostly dedicated to give you the context of noise control industry and also some fundamentals of acoustic. Then we will jump directly to the widely known standard ISO 15665. And to conclude this webinar, the 2 last parts will be the right time to share our design solution, but also share a concrete and real case study specified by my colleague Edouard. And by the way, I let know the floor to my colleague Edouard, which will give you more information about acoustic and the fundamental of acoustic. Edouard, the floor is yours.
Thank you, Fabien, for this introduction. Let's start with some first principles. We talk about sound and noise. What is sound? I think everyone recognizes what sound is. Listen to good music or watching a music. It's pleasant to hear and you have a pleasant sensation. But sound can also be annoying, and it can cause an unpleasant sensation, auditory sensation, or a bad perceived sound, and then we call it noise. But why we have to regulate the noise, especially at the workplace. Because if you are exposed to too much noise, it can cause your health, for example, hearing problems or increasing your heart rate. If you are in a too much noisy area, it's hard to communicate with each other. That's not only with talking and speaking to each other, but also you're maybe not able to hear detection of danger signals, which is quite important in industrial area. So in general, the noisy area leads to acoustic discomfort, which is tiring for human beings. So next slide, please. So here's an example how to regulate. What are the regulations to control the noise? This is an example from the European Union, which tells us that there is a directive, a European Union directive, which stipulates 3 stages of control of the noise exposure limit in the workplace. It regards the average noise exposure levels to employees, and then mainly during a specific working day or week. And there are 2 levels. There's a level of 80 dBA and 85. And if your exposure level is below 80, you don't have to take measures. Of course, it's possible, but you are not forced to. Is the exposure level between 80 and 85, then you're in the area of the lower exposure action value, which means you have to take some actions. For example, you have to provide hearing protection to your workers. They are not forced to wear it, but you have to provide it. And for example, another topic you have to do is health monitoring of your employees, at minimum on a 5-yearly basis. If your exposure level is above 85 on your own workplace, then it's mandatory for the workers to use and wear the hearing devices. And some extra actions are also taken into account, which means your health monitoring is not on a 5-yearly, but on a 3-yearly basis as a minimum. And for example, you have to place signposting in the noisy areas in your plant or factory. This is the 1885 is regarding the noise exposure levels during the working day. There's also 2 other numbers. That's 135 dBc, 137 dBc, which means for the peak levels, it's more related to pulse noise. They are the same actions you have to follow if the peak levels exceed this numbers. Next slide, please. The second thing we have to take into account is the noise to the environmental noise. The European Union has also written a directive to assess and manage environmental noise, which means noise emitted by, in particular, major sources like road and rail vehicles, infrastructure, aircraft, outdoor and industrial equipment, and mobile machinery. This directive is used by the different countries in the European Union, and it's the base for the local legislations which they make in their own countries. For example, it describes how to use it. For example, the exposure period in the day, night or evening. There are maximum exposure levels during this period, as you can see in the blue field, and noise level exposure from a factory to the surrounding dwellings will not exceed 45 dBA in the evening and at night. So if this level is exceeded, the factory needs to take measures to reduce the exposed noise. Next slide, please. So let's step into industry. How to control the noise in industry. The first thing we can consider is the controlling noise at the source. The second, controlling noise along the propagation path, and the third one is in the receiver. Preferred is to control the noise at the source, which means if you already have taken into account in design stage your noise control measures, you have less chance to take measures in the propagation path or in the receiver. So which means if you have to specify equipment, please take into account the sound power levels of the equipment, that kind of things. If you take a look to the noise control along the propagation path, Then we talk about airborne noise and structural noise, how to control the airborne noise, for example, to replace the location of the source or to place an enclosure around it, place silencers, absorption treatments in a room, for example, and so on. And if you take a look to the structural borne noise, you could place vibration insulation under machinery, floating floors, that kind of things. If we go to the last one, it's the noise control in the receiver. That's the last one you can take if at the source and at the propagation path is not possible. You can take measures in the receiver side. And the most common one is the personal protective equipment or hearing devices to your workers. But you can also decide to place a personal protection cabin in a noisy area in which the workers can sit and take rest or do their job. Regarding to the topic of today, noise control of pipes, it could be in two ways. It could be in noise control at the source, which means you are in a design stage of a project, or noise control along the propagation path, which means you have an existing project with a noise problem and you have to place an insulation system around an existing pipe. It's not so important in which way, but just to be clear. Next slide, please. So let's start with some fundamentals of acoustics. These are some parameters which are coming up in this webinar later on. Sound propagation speed, that's the speed of sound in a medium, for example in air, then the speed is 340 meters per second. Amplitude, it's the difference of the pressure. If you look to the right figure, the yellow one, you see a horizontal line, which means it's the ambient static pressure around us. And you see some waves written on it. On the left side, a low frequency sound wave, you see a long wave, and on the right side, a high frequency sound waves, short waves. And if you look into this figure, you see the amplitude. And the amplitude is the height of the wave. It's the difference between the ambient pressure. The higher the amplitude, the louder the sound is. And if you look to the wavelength, that's the length of a wave. That's called lambda, and the longer the wave, the lower the frequency sound is. For example, a drilling machine or the beat in music. And if you look to the right picture, you see more waves, shorter waves, which means it's high frequency sound, and like someone is blowing a whistle, that kind of things. That's the high tones. In acoustics, we don't present the wavelengths to present the tones. We use frequency. What is frequency? The relationship between frequency and wavelength is that the frequency is the speed of sound divided by the lambda value, which means you get a single number, and we can divide it in mainly three parts: low frequencies, mid frequencies, high frequencies. And low frequency from 20 to 400 hertz, you see the wavelength is up to from 17 to 0.85 meters. And you see by the mid-range and mid-frequency, high frequency, the higher the frequency, the shorter the wave is. The audible range of human beings is from 20 to 20,000 hertz, which means that's our range in which we can the frequencies hear. But there can also be sounds below or above this limit, and when it's below, we call it infrasound, and when it's above, we call it ultrasound. Next slide, please. Next is the dB level scale, the decibel level scale. Why are we using this? Not only the range of frequency is a big why, but also our human hearing range. Our ear can hear very little pressure differences to quite high pressure differences, from 10 picopascal to 100 pascal, which means that's a scale of 1 million times. That's a very large scale, and too large to make clear calculations, proper calculations. That's why the logarithmic scale is introduced, which means to obtain the sound pressure level, we have the real pressure, and it's divided by a reference pressure. we take the logarithm and then 20 times the logarithm of that number, then we achieve the sound pressure level. And the reference pressure is 20 picopascal, which means it's the sound pressure of the auditory threshold of human beings. If you look to the figure on the right side, as I'm talking now, I think I'm producing around 50 or 60 decibel sound pressure. And if you go up in the figure, you see a starting jumbo jet, then we talk about approximately 130 or 140 decibel, which is quite high and is also above our pain threshold of human beings. And if you are faced to levels above 140, you have seriously chance of losing your hearing system. Next slide, please. So, already mentioned frequencies. We already told that our frequency range is from 20 to 20,000 hertz, which is quite a big scale. And if we could only measure the frequencies with this kind of big scale, it's very difficult to handle and to make calculations and to make it viewable. So that's why the octave band is introduced. Octave band is a frequency range by a center frequency. And the noise is divided in different octave bands. If you take a look to the left corner, the octave band spectrum, you see from 31 Hertz to 16,000 Hertz an octave band spectrum, and you see only 10 bars, which means you have a clear picture of the sound pressure level in this figure. The center frequency, they are the numbers on the horizontal scale. For example, 125 Hertz, and there's a relationship in between 2 to 1, which means the next center frequency is 250, 500, 2000, 1000, 2000, and so on. But it gives you detailed information about the different frequencies or tones in a sound spectrum. If you want to read a little bit more in detail of this octave bands, very often is the 1/3 octave band is used. It's also it's basically dividing by 3 of the normal octave band, which give you more information. In this case, it's the same spectrum, but now it's divided in 30 bands, which give you more detailed information. For acoustic purposes, octave band or 1/3 octave band are the most common spectra to use. In some cases, when you need to find a specific frequency, the narrow band spectrum will be used, and then you are watching per frequency what is the detail of it. But that's for our case, octave band and 1/3 octave band is enough also for this webinar. Next slide, please. So now we step over to mineral wool, the most important parameters, acoustic parameters of mineral wool. One of the important parameters is the airflow resistivity. What is the airflow resistivity? It's the ability to reduce the transmitted acoustic energy by reducing the speed of sound in this material. If you look to the picture on the right side, you see the speed of sound in air. It's 340 meters per second. And when the acoustic energy hits the absorbing material, in this case mineral wool, the speed drops to 180 meters per second. And it's depending on the density of the material and also the fiber structure of the mineral wool. The ideal value for a mineral wool should be between 5 and 50 kilopascals second per square meter. If the airflow resistivity is higher than 50, then the mineral wool will more like acting a rigid material. This is an important parameter for the sound absorption properties of mineral wool. Next slide, please. So the next one is the dynamic stiffness of mineral wool. What is dynamic stiffness? Dynamic stiffness is the capacity of the mineral wool to act as a spring. When it acts as a spring, it's able to absorb noise and vibration. If you look to the pictures on the left side, you see a mass and is laid on a rigid material which is stiff. And the red one is an acoustic wave is incoming, and you can see that the hardly ever one is transmitted through this structure. And if you look to the right side, you have your same mass, but new placed on a part of mineral wool, which could act as a spring. Then acoustic wave is incoming, and you see that less acoustic energy is transmitted to the system, which means that this construction is insulating noise and sound. This parameter is an important one for designing acoustic insulation systems, also for pipe insulation. Next slide, please. Then we have sound absorption alpha. What is sound absorption? Sound absorption is the phenomenon that the incoming acoustic energy is hit by the material and is turned into heat. So, which means it will not be acoustic energy anymore, but heat. And this sound absorption coefficient can be between 0 and 1, which means if the sound absorption coefficient is 0, nothing is absorbed and everything is reflected. And if the number is 1, then all the energy is absorbed into the material. This parameter is an important one in acoustics, not only in industrial acoustics, but also an important one for the construction market, room acoustics, that kind of market. So it's an important factor and depends on several parameters like the airflow resistivity, the sound frequency of the noise, porosity. Here, that's the relationship between the air volume and the total volume of the material, the geometry of the material structure, and the thickness of the material. Next slide, please. So, insertion loss. What is insertion loss? If you look to the left side, to the box, you see a room with a speaker, a partition, and also a second room. Basically, it's a room divided by a partition. The speaker makes noise, and in this sending room, the noise is measured. So there should also be a microphone there. And in the second room, after the partition, the transmitted noise is also measured. And the difference between the levels of these rooms is the insertion loss. And it's depending on the structure of the partition. In this case, you can see a gypsum construction filled with mineral wool, but this could also be a wooden structure or a concrete part. The difference between the levels is the insertion loss. This is very common in the structural market, but this principle is also applying the industrial market with pipes. If you look to the picture right, the same principle is here. There's a noise in a pipe, and the noise outside, the transmitted noise outside the pipe, the bare pipe without insulation system, is measured. It's the reference level. Then in the second picture, an insulation system is applied around this pipe. The level in the pipe is still the same, but now the level outside the pipe is different, and the difference between the first case and the second case of the level outside the pipe is a measure of the performance of your insulation system, insertion loss. This principle, the standard, the 1565, is based on this principle, and my colleague Fabien will tell you a bit more about this standard.
Yes, thank you, Edouard. Yes, indeed, the explanation from Edouard is the perfect bridge to introduce now the ISO 15665, which exactly describes how we can measure this insertion loss. So what is this ISO 15665 about? So it's a widely accepted standard regarding acoustic in industry. It is commonly used for designing the acoustic insulation of pipes, valves, and also flanges. He has, of course, some equivalency at the national level, and I will mention here, for example, the ISTM E1222 standard, or even some link with the CINI specification, just to name a few of them. But the real specificity of the ISO 15665 is that he allowed to select the correct insulation during the design phase by implementing standardized classification. He put some North target to be reached using this classification, namely A, B, C, and D. Please note that the class D has been put in place by major company in oil and gas, like Shell, and it's a stringent and additional class to be considered when using this standard. Now let's discover the testing method. Basically, we try to define the difference in decibel between a sound power level radiated from a noise source before and after the application of the acoustic insulation, meaning here this insertion loss parameter explained by Edward just before. For this, there is 3 different rooms in the lab. We have first the room 1, where the loudspeaker unit is placed. Then we have the room 2 in the middle, where the measurement will be made. We also call this room the reverberant room. And finally, the room 3 on the right side, where you have the anechoic termination. Basically, the pipe is running through the room 2, and the acoustic insulation is placed in this room. And you have, I have tried to define in orange the insulation here. How we perform the test here, we measure how much the sound is radiating off the bare pipe, and then we run the same test over again, but by applying the insulation system. By comparing and subtracting the result from the insulated pipe, you will obtain the insertion loss in decibel, meaning the reduction of the sound level of your total system. Now, let's see how to use the ISO 15665 classification. These classes are mainly dependent on 2 main parameters. First, you have to select your pipe diameter, could be 1, 2, or 3. 1 for pipe with a diameter under 300 millimeters, 2 for pipe between 300 and 650 millimeters, and class 3 for pipe between 650 and 1000 millimeters. Then you could associate directly this diameter to the performance, namely your insertion loss, again, A, B, C, or D. For each octave band, the standard has set some minimal value per frequency, and by using this insertion loss value per octave, you can draw the reference curve, and you have a good example in the right side of the screen, where you have the reference curve for the class 3. Please notice the specific class D coming from Shell, as I mentioned before, is only valid for class 2 and 3, not for class 1, meaning for the pipe diameter between 300 millimeters and up to 1000 millimeters. The standard itself, also the ISO 15665, is only valid for pipe up to 1000 millimeters. Up to this specific diameter, only design or simulation can be used to ensure that you meet the reference curve. Okay, so here you have a table with all the value coming from the ISO 15665. So this is the insertion loss in decibel. So to reach a class, a given class from the ISO 15665, you need to satisfy all these values. So let's take an example here. So we take an example of a pipe diameter of less than 300 millimeters. To reach A1, it must satisfy the requirements that you have in green in your screen. And to reach B1, the one in blue, and finally, you have understand the red one to meet the C1 class. Maybe you have noticed in the table that you have negative numbers between 125 Hertz and 250 Hertz. Why? Because with an insulated pipe, the surface by square meter is bigger than with only the bare pipe, meaning the radiative surface is bigger. And that could have a negative effect on the acoustic performance by increasing the pipe surface. You can observe this phenomena, especially for A1, B1, and C1, where there is this negative number. Okay, now we have a good understanding of the applicable standard, this is ISO 15665, and how to measure the insertion loss of a specific system. Let's discover the practical solution coming from Saint-Gobain. So you have in the screen an extraction of the table for class 1 and 2 pipes coming from our acoustic industry brochure. These two tables give you all the details and the result for these two specific classes. The purpose of this table is not to bother you with a lot of detail, a lot of information, but just to show that we cover a wide range of products and solutions to fit most of the possible projects you can face in your daily business. One key information, all this configuration has been tested by third-party laboratories and reports are available upon request. Another point, in addition to that, thanks to the know-how of Saint-Gobain, we can modelize specific system for specific needs. Let's take an example of a pipe diameter up to 1000 millimeters. We can modelize. Let's think about a new mineral wool thickness. Also, we can modelize such configuration. Now, let's focus. We have seen the class 1 and 2. Let's focus on the class 3 pipe, meaning pipe up to 650 millimeters and reaching the D3 class. So the composition of the acoustic system is as follows. You have first a porous layer from mineral wool insulation, which is supposed to absorb the noise coming from the pipe. Then we have a mass layer, also called an anti-drumming layer. In a certain way, it's a barrier to the noise, as explained by Edward before. It creates a kind of damping effect. And then we have a closed cladding, which is a new barrier to the noise. But the main objective of this cladding is to, of course, protect the porous layer, here the mineral wool. This cladding could be aluminium or even a steel cladding. And finally, in the right part of the table, you have the result for each mentioned configuration. As you can see, for class 3 configuration, we have always include omega spacers, which is, of course, the common spacers in pipe system actually on the market. Why we have include all the time some spacers? First, because we wanted to know the real impact of the spacer and how we can improve this possible effect, how we can counter this possible effect. Second, because we wanted to have results representative to a real situation, because we know that for some configuration we need spacer, and this is the case, for example, for a wire and mat, especially ultimate. To handle the load of the cladding, we need spacer, so we need to test the configuration with spacers. And the third point is because we want to secure the long-term performance. If only the porous layer handle the load of the cladding, we know it could in a certain way affect the performance of the whole system. Let's now compare one traditional system versus our design Saint-Gobain system for a D3 class. Let's start with the traditional one. It's supposed to be, again, a D3 configuration. When you analyze in detail this configuration, we obtain 7 different layers for a total mass, approximately of 35 kilograms per square meter. It's clearly a heavy solution, and the main point, you don't have any spacer to support the metal cladding for such heavy system. So in the real life, you can clearly expect that you will have to install a spacer due to this total load. Meaning, in a certain way, you don't know the acoustic influence of spacer for this kind of system, which, in my point of view, could be clearly a blocking point. Let's have now a look on the Saint-Gobain system, also reaching the D3 class, and of course, testing in a third-party laboratory. Here we have one porous layer, 120 millimeters thickness of ultimate product. You have one mass layer directly glued to the cladding, 8 kilograms per square meter. You have alu or steel cladding, no matter. We have obtained the D3 class with both of this cladding. And of course, integrating the omega spacer to be representative of a real case. With only 3 layers and with omega spacer for a total max of 16 kilograms per square meter, we have reached the top class D. So my main message here is standard and ISO 15665 give you a direction, but it's clearly possible to improve and design specific insulation system more practical and more performant. Second point, prefer real test, including spacer, because even by choosing a traditional system, you are not sure to achieve the class mentioned, because here you don't have any spacer included in this traditional system. Now, let's compare the test result obtained on a real test report versus the ISO 15665 generic classification. So again, to reach a class, insulation material or system need to meet or exceed the reference curve. Taking an example that you have on the left side of your screen, we can clearly see that the red curve is clearly exceeding the reference curve. The reference curve is the one with the X blue on the screen, meaning the system performed clearly better than the limit value given by the class C. So with the green zone or blue zone, I don't know really, you can perfectly notice the gain you will have between the reference curve and your real test. What does it mean finally? That means for a specific project, this precise data can be considered. I just invite you, to contact your local representative to get the best possible solution depending on your project constraint. And by the way, I will now let the floor to my colleague Edouard, which will present a real case study, and you will see how it's perfectly aligned with the designed solution offered by Saint-Gobain. Edouard, the floor is yours.
Thank you, Fabien, for this part of the webinar. Yes, I'm going to show you a project which we have done in the Benelux, and regards noise pollution of in the surrounding of an industrial plant. And in this case, objectives of the local residents were there. And there was an acoustic engineering company hired by the plant owner was involved to investigate the location of the source and the proposed potential measures which needs to be taken. And we, as Saint-Gobain ESOFET Technical Installation, supported the plant and also the contractor to select the most suitable installation solution in this case. Next slide, please. So, some background regarding this project. On the right side, you see a picture with a red circle. That's the plant. And you see some yellow numbers in the field. There are the measurement points and dwellings in the surrounding. And first step was to take sound emission measurement in the surrounding by the dwellings. And this was done by the engineering company. And they discovered that the audible tones in 800 and 1600 hertz were measured at these dwellings. They did the measurements in 1/3 octave frequencies. And it results that the sound levels at the dwellings was from 37 to 46 dBA, due only to this tonal components 800 and 1600 hertz, which means it was an exceeding of 6 dBA minimum in the night period. And it was already a strongly suspect that an industrial fan at the plant could be the main source of this noise pollution. Next slide, please. So the next step was to verify the source in this plant. So the engineering company took a sound intensity measurement at the suspected fan installation, and they measured the noise enclosure and the engine of it, sound power level of 90 dBA, the inlet piping, and a sound power level of 119, outlet piping 118, and they also took some measurement in the surrounding of the installation, the oil tank and appendages, but it had no contribution to it. So the total sound power level of this fan was 122 dBA, but the main sources of the noise was the inlet piping and the outlet piping with the numbers of 119 and 118 dBA. So the next step was to make the verification. Is this the source who causes the noise pollution in the surrounding? So the engineering company make a model, a digital model, to predict the sound levels at the dwellings with this data, source data, as an input. And the conclusion was that within the measurement accuracy, those two pipes were the main sources of the measured sound levels at the dwellings. So the source of the problem was found. Next slide, please. So the engineering company specified an insertion loss for the pipes that they had to take measures around the pipes with a minimum performance of insertion loss per octave band. They didn't use the standard. They decided to go to give a spectrum per octave band, a dB value per octave band. And at the time that we stepped in this project, there was already an existing proposal with wide mats, thermal wide mats, and a combination with mass layers. As you can see, it looks like quite the same system as Fabien presented. It's a mineral wool with mass layer, again a mineral wool layer, and then 3 mass layers and a steel cladding outside, which is a quite heavy system. And that was the weight was also one of the barriers in this project, because due to the weight of this insulation system, the loads on the pipes and some parts of the existing construction became too high, which means that they had to place extra support construction, and also rings were needed due to the high weight of 39 kilograms per square meter. Support rings were needed because of the strong weight of the insulation system, and because of this weight, the rings need to be welded at the piping for carrying the whole insulation system, which is quite complex in this case. And also the thickness of 150 millimeters was quite big, because not everywhere was this space available around these pipes. And the last one, the installation time. If you have to install 7 layers and also support rings, it costs you quite a bit of time, which means that also your shutdown time of your installation is also quite long. Next slide, please. So we decided to go for an alternative. And to reach this, we made several calculations with different insulation system. We took the 1/3 octave frequency spectrum from the engineering company, and we made calculations with several systems. And we decided that a system with ultimate mineral wool, 100 millimeters, including omega rings, which was tested in this setup, because we know the influence of this rings on the final performance, and an aluminium cladding including a mass layer glued on the inside of it, which means that we have reached a lightweight application, approx 90 kilograms per square meter, compared to the proposed one with stone wool wide mats. It was 50% less weight, and also 100 millimeters instead of 150 millimeters. And as already mentioned, this system was tested including omega rings, and these rings were also needed for this system, so we know the effect. Last thing we had to check was the validation of this test, because these pipes, the inlet and the outlet pipe, 1.2 and 1.4 meters in diameter, is bigger than 1 meter. So we did a check at our research center of Saint-Gobain. They model the system, and they conclude that the measured values are valid for this kind of system and diameters. Next slide, please. So we have delivered this system. This system is also installed by the contractor. After the installation, the engineering company took also measurements in the surrounding at the dwellings, and they conclude that the sound levels at the dwellings are now fulfilling the legal exposure levels. So that's point 1, but also the tonal components were disappeared, and the problem was solved. And this results that the local residents have withdrawn their objections in this case, which was quite a relief for the plant owner. If you look a little bit further for sustainability reasons, then you can conclude that this system, compared to the first proposed one, has 60% less use of raw material due to the weight of the raw material, and also less waste on site, means plastics, pellets, etc., because you have to use less materials. Then from the contractor's point of view, safety, installation and construction, we had a minimum installation thickness, 100 millimeters instead of 150, and also 4 to 5 layers less to install compared to the proposed system, and also no additional mass layers in the field they had to install, which means they had also a less shutdown time for the installation, because the installation was quite faster compared to the traditional one. Also, the total weight is 50% less weight compared to the traditional one, and there was also no need for welding the support rings in the construction. They could clamp it around the pipe, which is also an advantage in this project. And the last one, the logistics, due to the use of less materials, were also less packaged to transport, not only in the truck on the road, but also less packaged materials to transport over the scaffolding in the field, which means it's a safer installation in the end. If you want to read more about this project, we have published this project as a reference project at our website. So I give the word back to my colleague Fabien.
Thank you, Edouard. Yes, so as a conclusion of this webinar, let's see the good reason to choose a Saint-Gobain solution. So first, the lightweight, which has been perfectly described during our session and confirmed by the real case of Edouard. So we are 15 less weight in terms of weight than the traditional system, and we have minimal also layer. It's for sure easy to install and better in terms of logistics. Third-party verified. All our tests has been made in a recognized third-party laboratory. Best-in-class solution. We have reached, of course, the top-class D3. Real case solution. For each configuration, we have designed our solution to be representative of a real situation. And the good example is here for the spacers, considered for all tests. And finally, tailor-made solution. We provide optimized solution for designer with a full range of tests, modelization on request to fit most of the project constraints. And in addition to this, we have also created a specific acoustic selector that allows you to choose the best configuration for your project. And here I invite you to check the technical insulation website. Let's jump to, and to conclude this webinar, let's jump to a short Q&A session, and let's try to answer all your questions. Okay, so Edouard, we have a first question. I think I can take this one. So thank you for this webinar. You're welcome, of course. You include the Omega spacer rings into your system. Does Saint-Gobain sells these Omega spacer rings, Omega rings? So no, we do not sell as Saint-Gobain Omega rings. There is several manufacturer and supplier of this kind of material. So it's mainly depend of the country, and all the country have different supplier for this. As this is a question looking at the Omega rings, I don't know if you noticed, but on one side I mentioned one specific spacers, an innovative spacers. And for you to know, we have designed at Saint-Gobain a specific spacers, although to even not have a negative effect on acoustic, but even a positive effect on the acoustic result. So I invite you to know more about this design spacers to contact your local representative. Let's check if we have another question. Did you test glass wool system also? Edouard, I think you can take this one without any problem.
Yeah, okay, thank you. Yes, we did. As Saint-Gobain, we provide multi-material, glass wool, stone wool, and ultimate. And we did test some acoustic performance of glass wool systems, but the main focus, the first focus, is on stone wool and ultimate system, because due to the high temperature needs in industry, so we would like first to test system which you could apply to the whole temperature range from, let's say, cold, low, and high temperature. So, as a summary, yes, we have tested some systems, but we have tested more systems with ultimate and so on.
Okay, Edouard, we have one next question. Do you offer tailor-made solution given that each, okay, it's changing, sorry. Can you go back to the last question? Okay, I will, do you offer tailor-made solution given that each scenario is specific and maybe not covered by the configuration already tested? Edouard, do you think it's, you can answer that one also?
Yes, we have done a lot of tests with most common setups, but of course, as I told you in the reference project, in some cases you have another system or your pipe dimensions is different compared to the test. So yes, we offer engineering services to modelize the acoustic performance of an installation system. Then we need all the details of the system, and we can make a calculation. Yes.
Yeah, exactly. Thank you, Edouard. Do you have a thinner solution when there is a lack of space in certain areas? I'm not sure to exactly understand the question. Do you have an answer for this, Edouard, also? Do you have thinner solution when there is a lack of space in certain areas?
It depends on the requirement of the project. But if you look to the, I would say, yes, we have, and it's related to maybe to the topic you already mentioned in this Q&A session, that with our solution with the acoustic spacer, we can achieve a thinner solution with a high performance. So yes, we have the option to decrease the installation thickness with equal performance.
Yeah, I will add something here, maybe, Edouard. Yes, sure. As I mentioned before, we have a design solution for a specific system. We have a new spacer able to reach really good results in terms of acoustic. So we can implement in a certain way all the know-how we have gathered during several campaigns to try to define the best solution for your constraint and for your project. Could be a thinner solution, as you mentioned.
Yeah.
Hello, my question is, did you test other type of cladding material than steel and aluminium? Thank you. For the time being, we have only tested steel and aluminium solution, but why not testing other kind of cladding? We are focused, of course, our test and our program on the most common cladding we face on the market. But for any kind of specific project, we can modelize or even test a new possibility of cladding. Edouard, if you want to add something here.
No, I think you're perfectly right. Our main focus is on the most common cladding types, which is aluminium and steel in industry. And of course, if we have the properties of the proposed cladding, we could make a model.
Exactly.
Or test. Yeah.
Okay. Okay, next question. I think this one is for you, Edouard. Could you provide brief explanation difference between sound pressure level dBA and sound power level?
And what?
Sound power level.
The sound pressure level and the sound power level. Okay. Yeah, the sound pressure is air which is reaching our ear, and if you look to the sound power level, it's the power of a source. It's not. We cannot really hear the sound power level, but it's the energy of a source in a sound source, and it's radiating the sound pressure level. That's the difference.
Okay,
thank you. I will be a little bit clear.
Okay, thank you, Edouard. what are the advantages and disadvantages to use a spacer or not? Okay, I will start and then I think you can complete, Edouard. I will say you use spacer mainly to handle the cladding due to the load of possible cladding. As we are speaking about acoustic, I would say the main disadvantages of a possible spacer is to have a negative effect on the acoustic results that you will obtain through the ISO 15665. Yeah, I will start like this, and Edouard, I'll let you add something if you had to add one comment to this information.
Yeah, when you look to mainly bigger pipes, and then sure, in the case of used blankets, in almost every case you have to use spacer rings to carry the cladding, the weight of the cladding, because not all the mineral material is suited to carry the weight. And indeed, yes, there is it could be as there is an understanding that the spacer ring could be an acoustic bridge in the system, but in reality, spacer rings are very often needed mainly for bigger pipes and blanket systems. So that's why we decided to set up the tests as a real case as much as possible with and including the spacer rings.
Okay. Thank you, Edouard. Can you tell me what kind of services do you provide? Do you have any tools to accompany customer in the selection of the best solution? Oh, okay, really good question. By the way, I just mentioned this information at the end of the webinar. We have in our technical installation website an acoustic selector, which allow you to select through all the configuration we have the best solution for you. So you can use this tool. It's free and available on our technical installation website. We have also, as a service, we have also, of course, our technical brochure available on the technical installation website. Please add something, Edouard, here if you see another services.
No, you're right. We have the selector at our website. We have our brochure regarding acoustics, and also it's more a bigger document, our technical industrial manual, which describe the acoustic installations also a chapter.
Okay, thank you. Other question, is it possible to resend this presentation? Yes, of course, this presentation will be shared. I don't know exactly when and where, but probably through our social media. So please stay informed through LinkedIn mainly, and probably also on YouTube. You will see with or we will share this presentation. But as you are registered with this webinar, of course, you will receive the final presentation. And I think we have no more questions. I just check. It's done. So, okay. So thank you for all your questions. We have provided a suitable answer, and that also you have enjoyed this webinar. So the session is now finished. Thank you for your attending, and of course you will receive the link after to review this presentation. See you soon.
Thank you. See you soon. Bye.
Bye bye.